Hello, my name is Kunal Khallar, and this is my project on adversarial attacks. The idea is that a neural network can score 98% plus accuracy on clean data and still be broken almost completely by pixel changes a human eye can't even see. So, I wanted to measure exactly how bad that gets, and then measure how much a standard defense actually fixes it. So three things happen here in this image. First, I train a normal CNN digit classifier. Second, I attack it with two standard methods, FGSM and PGD, and track how its accuracy collapses as the attack gets stronger. Third, I train a second model using adversarial training, where the attack is baked into training itself and compare the two head to head. Alright, let me walk through the code. 7 files, each doing one clear job. Model.py. This is the network, two convolution and pooling blocks, then one dense layer. I kept it small on purpose because the defense step later restrains this architecture many times, so it needs to be fast. Next one is attacks.py. Um, so this is the core of the project, the two attacks. FGSM that computes the gradient of the loss with respect to the input image, not the weights, and then takes one step in the direction that makes the model more strong. The PGD, on other hand, does the same thing but repeats it in small steps, correcting course each time and staying inside a fixed pixel budget, much stronger than one big step. The next one is train.py. Uh, This is the defense. On every single training batch, I generate a fresh PGD attack against the model's current weight and train on that adversarial version instead of the clean image. So the model is constantly being shown its own worst case, learning to get it right anyway. The next one is evaluate.py. So this sweeps attack strength epsilon from 0 up to 0.3 and records accuracy for both the models under both attacks at every step. This is what produces the actual number, and I'll show in the demo later. The next one is visualize.py. So this one turns those numbers into two figures that matter, the accuracy curve and a side-by-side panel of real digits before and after being attacked. The final one is run pipeline.py. So this ties everything together, all these files together in one command. Train the baseline, train the robust model, runs the full sweep, save every figure, and yeah, that's the whole project end to end. So now let me show you the live demonstration. To run the pipeline, we write python run pipeline.py, and it starts executing the pipeline step by step. This will take some time. This trains both the models and evaluates them. This will take a few minutes, so I'll just speed it through. All right, it's done now. You can see the baseline model, it's 98.2% accuracy on the clean digits. Now watch what happens under the attack. Let's see the epsilon sweep PNG. This is the headline result. The red is the undefended model. The green one is the adversarially trained one. At the strongest attack I tested, the baseline drops to 15% under FGSM, barely better than guessing, while the robust model holds to 58.7%. Under the stronger PGD attack, the baseline falls to 26%, and the robust model holds to 72.5%. One thing that I didn't expect at all is that at very small attack strength, the baseline is actually still more accurate than the robust model. The crossover only happens around epsilon 0.05 to zero point 0.1. So the defense isn't free and it isn't universally better. Now let's see the attack examples. So here's what that actually looks like same 5 digits attack with FGSM. To your eye, these looks identical, right? But if you see uh, the 4 gets misclassified as 9. That's the whole danger of this attack. The input barely changes, but the prediction flips. So the undefended models are more fragile than their accuracy number suggests, and the adversarial training measurably helps at a real cost. The full code and the report are linked in the description and also uploaded in the internship portal.